All right, so I did actually get a request to go over some problems. So give me just a minute to look up this problem. It does take a little while to get through the Connect software. But specifically, I got asked about questions 14 and 15 on the test one homework. So now keep in mind with the Connect software, it does use randomized pulls for some of these questions. So if I'm on question 14, you're like, that's not quite the problem I got. It's probably just selecting another random problem from the pool. So question 14. General molecular formula for alkanes is C4H2. What is the general formula for a cycloalkane? And this actually comes from the hydrogen analysis. We haven't quite gotten to this yet. So let's say you have some alkane, CnHY, and you hydrogenate it with H2. And the thing is that there is a general formula for alkanes that for a saturated alkane, Y here is going to equal 2N plus 2. But we can lose hydrogens due to double bonds and due to rings. So we'll lose 2 for every ring and 2 for every unsaturated bond. So let's say we have the formula C10H18. And the ideal formula here is for H to be 22, so where do the 4 hydrogens go? Well, there's two possibilities. They're either in a ring or they're in the unsaturated bonds. And the way we would measure that would be you'd expose it to hydrogen, and we measure how much hydrogen comes out, how much hydrogen is used. So if we use 0 moles of H2, it's 2 rings. If we use 1 mole of H2, it's 1 ring. And if we 2 moles of H2, it's 2 rings. So in this case, what is the general molecular formula for cycloalkanes? It's just this 2N with no 2. So here, if we had a ring, it would just be CN2N. It's a little bit more towards the alkane stuff, but this is actually meant to kind of play into, we'll talk about hydrogen uptake later in the course. And that's a way to figure out if you have an unsaturated hydrocarbon, how much of that unsaturation is due to rings and how much of that unsaturation is due to double and triple bonds. All right, question 15. In general, what is the molecular formula for an alkene? Alkenes, same line of reasoning. If you have an alkene, you typically have -2, so you're going to have the CN to it, and it's the same line of reasoning. Again, this is all boiling back to the hydroanalysis. You probably haven't gotten to that point in the notes. It's kind of a funky analysis. I'm not a huge fan of it, but we do teach it because some people still use that technique. So that's it for all the questions I had. Sorry, I was expecting that to take a lot longer. I don't have any concurrent viewers right now. Well, maybe I have one, but as with all these live streams, these are office hours. These are not lectures. If you have questions, please feel free to type them into the chat. I got a few emails I want to send off this morning. So I'm going to turn off the video. If you have questions, post them to the chat. I'm definitely here. There's about a 45-second lag between when you type and when I see it, and then a 45-second lag between when I respond. So potentially up to a minute and a half, but definitely your questions are being seen. So leave a message in the chat. Otherwise, yeah, don't really have anything else to talk about today in office hours. All right, so just got to ask a question. For Newman projections, why do we change the ways atoms are arranged when we look at the structures from right to left and left to right for wedged and dashed bonds? So this is where a modeling kit's going to come in really handy. So I'm going to take a 4-atom carbon backbone, and to make it easier for you to see, I'm going to use 4 different colored atoms. So the way this is going to be drawn is I'm going to have yellow coming out front, blue coming out front, red going back, and white going back. And now I want to draw a Fisher projection, but with the Fisher projection, there's actually, what you're doing is you're turning the molecule and you're going to look at it down one bond. So in this case, I've got the eclipse conformation. So if I make this the front atom, so I've got my yellow and my red, the way I'm going to do is I'm going to turn it 90 degrees. And you can kind of see it in the camera here. Sorry, it's a little bit hard to position the camera. This is what you get. So you're going to have yellow, red, and the atom down, and behind it, you're going to have the white, the blue, and the other group. So in this case, all the wedges are on the right side and all the dashes are on the left side. But let's say I want to look at it with this being the front atom. Well, now when I turn it, I've got the blue going to the left, white going to the right, my group going down, and if I look on the other side, I've got yellow and red. So these have switched places simply because I've changed what the front atom is. So if this is the front atom, all the wedges on the left side. If this is the right atom, all the dashes on the back. The nice thing is that wedges and dashes always appear on the same side. They'll appear on the right side, all on the right side, or all on the left side, depending on how you turn the molecule. But the reason why wedges and dashes don't really have an implication on left and right is it's a matter of which way you got to turn the molecule in order to get that front atom front and center. Now, that said, we do kind of have rules. So anything that's vertical, that's just a solid line. So anything that's got kind of the solid line to it, again, there are exceptions to this, particularly if you look at the practice packets. There's some like weird ones where you're doing it across a wedge line. I would really recommend you build them with the model kit and then draw them that way. But generally speaking, on a very simple projection, anything that's a solid line up and down, this is one that's drawn down. Anything up here is drawn up. And again, your wedge and dash are going to depend on how you rotate it. But the thing is, all the wedges and all the dashes have to be on their respective sides. So we can't flip red and blue here. They can't ever be on the same side because one is wedged and one is dashed. Yeah, this is where your modeling kit's going to come in really handy, because this is really all a Newman projection is taking them and looking down the bond angle. And if we were to draw a staggered conformation, which is this, it's a little bit easier. There we go. You got the front atom, blue, white, black, and then the back atom going up. These would all be solid on the board, and then you have your wedges and dashes. Yes, I would highly encourage modeling kits. This is going to especially show up when we start doing Fisher projections. So the issue we have, I shouldn't say an issue. So when we draw the lowest energy conformation, so the conformation being when we just rotate around single bonds, So let's say I draw this. This is the most stable conformation because all the bonds are stretched out. This is not the way the Fisher projection is. The Fisher projection would actually look like, let's see here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we'd actually have to rotate these bonds in order to make it look like an actual Fisher projection. So this is actually what the Fisher projection is showing. It's not showing this actual staggered conformation. So it gets a bit more complicated when you take a normal skeletal drawing and you try to bring it over to the Fisher projection. And this is where your kid's going to really help. Or should we follow the study packet? Study packet is arranged in what I think is the easiest way to learn the material. The book, so we teach, particularly here, the first test is going to be scattered throughout the book because Francis Carey likes to break the characterization up through the chapters. We don't think that's highly effective. We think it's actually better to do all the characterization. So when it comes to the book, definitely when we get to test 2, that's when we're going to start getting back to following the chapters of the book. So chapter 2, 3, I think 4, 5, 6, 7, and 8. But right now we're having to jump around because we're focusing on characterization, and Francis Carey scatters that characterization throughout the book. So I would follow the study packet, and in terms of pacing yourself in the course, each week there's going to be an announcement that comes out that says these are the topics you should be covering, and the discussion board will give you a feel for that as well to say, okay, this is a type of question you should be able to answer this week. The hardest part with pacing a course, and this is kind of true of any online course, but especially with organic, we're starting to see differences in background, and we're also starting to see differences in proclivity. So like stuff you really kind of like catch on to and sometimes you don't. So in a classroom setting, ideally we don't have like a rigid, we're covering this today, this tomorrow, this the day after. What we do is that we pace the course based on the student response. So if you hit a topic and like all of you are just really kind of getting it, we're not going to spend a whole bunch of time on it. We'll move on to the next concepts and make sure we have enough time for the concepts that are going to take more time. Each class is different. Each student is different. So with an online course, I can give you a recommended pace, but the hard reality is some of the stuff you're just going to pick up on immediately and some of the stuff you're not. So I've tried to pace it out with the discussion board and the announcements. Everything on that study packet is going to be on the exam. So work through the study packet as best as works for you. You can definitely jump around on those packets. So if you hit a topic and you're like, I'm just really not getting it, you're free to move on to the next topic. In fact, I would encourage it. So take a little break from that topic, move on to the next one, and then come back to it when you've kind of like decided, okay, I'm ready to pick up on it again. But it's really hard to tell students how to self-pace a course because you're all a little different. Some people just immediately NMR clicks and they're able to do it really fast. Some people will still be on going to the final exam and they're still really struggling with NMR. I can give you a suggestion, but that's all it is. It's just a suggestion. Other questions out there? Hybridization problems. So this is another point where functional groups come in real handy. So and you'll see this summarized in the notes, if we have a CH3, CH2, CH alkane, these are all sp3 hybridized carbons. Hydrogen just has an s orbital. If we have oxygen with 2 bonds, it's sp3 hybridized. If we have carbon with a double bond, it's sp2 hybridized, and if we have carbon with a triple bond, it's sp hybridized. So let's say we have the following molecule, and I have to draw the hydrogens for this example. We just look at the functional group. So this carbon is a CH3. It's going to be sp3 hybridized. This is going to be sp2, sp2, sp, sp, and hydrogen only has, we'll throw an oxygen in there. We have oxygen, so oxygen here is going to be sp3, and our hydrogens are all going to be s. So to describe any bond, so this HC bond here, this is a hydrogen S to a carbon sp2 bond. When it comes to this carbon oxygen, this is a carbon sp to an oxygen sp3. This is a carbon sp to a carbon sp, and this bond here is a carbon sp2 to a carbon sp3. So that's how you approach it. Again, this is kind of why we use the functional groups. Based off the functional group, we automatically know the hybridization as well. So once we know the hybridization, we don't have to worry about rederiving it. You could rederive this from Lewis theory. There is a way to do it based on the AXE notation. So if you're taught AXE, and I teach my students AY, you can prove it for all the cases, or you can just memorize it. A 4-bonded carbon is sp3, 3-bonded carbon sp2, 2 bonds, or 2 periphery atom carbon is sp. Oxygen is pretty much always sp3 if it's got 2 bonds, and hydrogen is always the s. Yeah, this is why so this is the backbone of organic chemistry. You're going to work smarter, not harder, with a lot of these derivations. Yeah, you're welcome. So particularly with organic chemistry, the goal here is to make it as simple, that's the German roots. We're going to make it as simple as possible and very straightforward as possible. So we can try to rederive it for all of them, or we can just memorize the base cases knowing that this is pretty much 90% of these cases here. Especially when we get to the naming, like you always read the naming right to left. Once you see that and you can't unsee it, the naming gets really easy. Even with alkanes, it gets really easy to name. All right, other questions out there? Do you have solutions to the book's solution manual for the in-chapter problems? I honestly don't know. I would hope so based on what you have to pay for it, but it wouldn't also surprise me if McGraw Hill doesn't give you access to it. Um, yeah, to be honest with you, I don't know. I would assume they would provide it with you, especially with the ebook, because with the ebook, that's kind of the adaptive learning that you should be able to click on the problem, work on it, and it should tell you if you're right or wrong, or tell you what the solution is. So my guess is probably. I know the physical copies you had to buy a separate solutions manual, and like there was like one person that had it and it just got shared. At least was my experience in college. And unfortunately, it does technically give me a student view of the textbook. Full disclosure, particularly with the Connect software, the student view is absolutely awful. Half the times it doesn't even recognize me as a student in my own course. They're not passing the buck here. It's just that the answer to your question, I don't know because I don't see what you see on the student end. I would hope so, but it wouldn't surprise me if they didn't. If you ever have a problem that you can't solve or you're curious what the answer is, just shoot me an email. I can tell you what the answer is. I can work it out. Other questions out there? I know there's a lag. All right, I'm just going to put up the blank screen again. I'm still here, just getting a little bit of work done. Man, that lag's annoying. What is the best way to start off interpreting Esp maps? So, electrostatic potential maps. Let's say we have two atoms, A and B. And we're going to have EA be electronegativity A and B be electronegativity B. So we got three scenarios. We have easiest scenario is electronegativity A equals electronegativity B. So what you'll see in the electrostatic potential map is pretty much a green color. Now, if A is more electronegative than B, it means it's going to grab more electron density. So we see this, really, do I not have a red pen? There you are. We'll see this as sort of a red coloring on A, and then green is kind of an intermediate electron density. Then blue means lack of electron density. If we have electronegativity of B being greater than A, we'll get the reverse coloring. Yeah, you can see that. So the way you read an electrostatic potential map is blue, we're going to refer to as delta positive. It means a slightly positive charge. Now, when we say slightly, this is relative to a pure ion. So B probably is not like a cation, but it's definitely positive enough to attract a negative charges. Delta, the red color here refers to a large buildup of electron density, and so we would say this is delta negative. So it's not a full -1 charge, but it is negative, so it will attract the positive side. Green here refers to a charge of 0. So we would say that this is the nonpolar or NP regions of the molecule, whereas the red and the blue are definitely the polar regions. Now you always transition from blue, green to red. So you'll always see like a green sliver in a molecule, but the bigger this electronegativity difference is, the more pronounced it gets. So this is something where they're kind of different. So this would be like sulfur on one end and nitrogen on the other. But let's say you had an OH bond. In this case, it would look like this, with a very thin sliver of green running between the two. So the less green we see and the bigger color differences, the more intense red and the more intense blues we see, that's the more polar part of the molecule. Now, this is something that was supposed to be addressed in chemistry too. It depends on the structure you had. Polarity at the Chem 1 level is taught as binary. Something is polar or nonpolar, and that's not true. The world is not binary. It's a true spectrum. So a truly nonpolar molecule is hydrogen. That is the only example of a truly nonpolar molecule. You have two atoms, same electronegativity, and there's no symmetry difference in their electron density. So it's two spheres. There is clearly no positive or negative charge. The rest of the diatomic gases are as close as you're going to get to a pure nonpolar molecule. The reason why we can say that they're not quite nonpolar is because those sp-d orbitals in them actually do give some gaps in the electron density. But for all intents and purposes, they're the only ones that are truly green. Now, we can have the other extreme, which are ions. So sodium chloride, lithium fluoride, things like that. Those are truly polar molecules because there's a true charge separation. Between the two, you have hydrogen bonding, where hydrogen is given off by oxygen to another oxygen, so we end up creating these intermediate ions. So water is an example of this. H2O will dissociate into H plus and OH minus. It's a very small number of atoms, but they do it. Yes, so the middle molecule here, an example of this is a diatomic gas. So F2, H2, Cl2, Br2, I2, O2, N2, all examples of something that would give you a shape like this. Now, when I say it's a spectrum, if we look at, okay, so I drew this OH, but I can have a carbon chain hanging off of this. So if I have a CH2 group, even though there's electronegative difference between carbon and oxygen, the CH group here is going to look green. And if I keep tacking on CH2 groups, I'm just going to create a longer and longer chain of what basically amounts to a nonpolar molecule. So if you look really close at electronegativity map, it does get a little bit towards the blue end with the hydrogens bound to the carbon, but you're not going to see like blue and red with the carbon and the hydrogen. You're going to really kind of just see this green color with some yellowing in there, just because yellow, I think, is the intermediate between the green and the red. So this end of the molecule is polar, this end of the molecule is nonpolar. And if we start adding more and more nonpolar functionalities, it's still technically a polar molecule because of this OH group, but it's really much more nonpolar because of how much it is. So this is how we read Esp Maps, is it will tell us where the polar part of the molecule is and where the nonpolar part is. And the amount of green will tell us basically how polar the molecule is relative to like something like water, which is definitely going to have like that true charge separation. So the more green we see, the less polar the molecule. The more blue and red we see, the much more polar the molecule. And these colors refer to electron density. So blue refers to like no electron density, red refers to tons of electron density, and green's just kind of an intermediate true covalent bond. And also kind of clarify, when we talk about nonpolar, some people try to quantify this, and it's very hard to quantify these things. They will describe differences in electronegativity as defining whether or not a bond is polar or nonpolar. This is not a good way to do it for a few reasons. So this is a polar bond. Carbon definitely loses the war to fluorine, but carbon tetrafluoride is a nonpolar molecule. And so if we drew the electrostatic potential map of this, it would still look green because all the electron density is on the outside. But if we did something like this, where we switched to a hydrogen, we would definitely see a large amount of electron density sitting by the fluorines. And poor old hydrogen being bullied out of almost all its electron density. It's just a better way to look at polarity. Correct. So when you look at these maps, the only thing is like, can you identify the polar? Because again, this polar-nonpolar definition really is a bad definition. It works for simple molecules like it does in Chem 1. So in Chem 1, you work with one central atom, potentially 2 or 3 depending who taught you, but most of your examples are one central atom. You can say polar or nonpolar. But if we deal with something like a lipid has a carboxylic acid in. That's definitely polar and it acts like a polar molecule. but the rest of it's nonpolar. It's a long chain alkane. And so this is how soap works. Soap forms the micelles. The micelles come from the nonpolar ends binding to the organic components and the polar end binding with water. You end up getting these basically balls of long chain fatty acids. But if you draw the Esp map of, and you can do this actually, I think it's in the software that I linked to. So yeah, if you go to mole view, you're welcome. So I'm going to bring up mole view for you. And so this is mole view. It's freeware software from, I think it's the Department of Energy or NIH. So I've drawn this long chain fatty acid here. So this is the carboxylic acid. Here's the nonpolar group. We can do the electrostatic potential map. Where are you? Yeah, I know. In fact, this is where I got them from, was this website. Maybe it won't do it for me. Sorry to say it's been so long on this, but it should be showing up. I don't remember quite how you do it. Oh, that's right. Actually, it's fine to do the structure as it is. Okay, gel mold. So if you look at these two molecules, let's see if it's going to work for me. So you have something like ethane, it's purely green, even though the carbon-hydrogen bonds have different electronegativities. But it's all green. This is a nonpolar molecule. Whereas if you look at the carboxylic acid beside it, like you see the red here due to the oxygen's pulling electron density off. You have a blue from a hydrogen, and there's a little bit of electronegativity pulling that first carbon. But the rest of this molecule is definitely nonpolar. So that's what the CSP map is telling you, is that this far right here is the polar in the molecule. The rest of this is nonpolar, and that this molecule up here is definitely nonpolar. Now, if I clip off everything, and then I do my ESP map again, you can see that this is definitely a polar molecule. Like, there is some green just because you have the transition barrier between red and yellow and red, or what, blue and red is going to be that green color. But you're not going to see large areas of green here. This is definitely a very polar molecule. But yeah, MoleView is free software. Build molecules. You can see how they move the electron density around. I think there is a link to it on the course website. But it's how I built all the maps for the course. Make sure this is the right link before I send it to you. Yep. It's a little clunky to use, but All right, it kind of looks like it for questions. So again, these are office hours, they're not lessons. So if you have questions, feel free to email them in advance. Again, you kind of see from the chat today, it's what's here for. These are always loaded, so this way you can see them or go back to them. All right, I will talk to you all Monday. Have a good weekend.